All right, good afternoon. Announcements first. I think you must have seen the change that I made to deadlines of homework 7 and homework 10. So I found that homework 7 is around exam 2, but its deadline is 1 day after the deadline of exam 2. So I extended its deadline to 2 days after the deadline of exam 2. So even if you don't study, let's say you don't pay attention to homework 7, so after the exam 2 deadline, you will have 2 days to work on exam 2. I think that must be enough, considering that I give only 4 questions, so must be enough. In total, I give you for a homework 7 10 days instead of 8 days. So it must be enough. Homework 10, it's even worse. Like homework 10 and exam 3 were both due on the last day of the semester, December 7th, 11:59 p.m. But then it would be problematic to do both of them at the same time. Some people might run into trouble. So I decided to shorten the period of homework 7. So it will have you'll have 4 days, and it will be due 5 days before exam 3. But so to reduce the amount of work and guarantee that everyone will finish on time, I will ask only 2 questions in homework 10. So it will be a small homework. All right, its weight remains same, but just since I give you 4 days, I reduce the amount of the work that you should do for the homework. So 2 questions instead of 4 or 5. Exam deadlines remain same, so it's all announced. So just please pay attention there. I'll remind from time to time. Okay, looks like 10 homework simply is a killer. You can't set up things in such a way that before the exams there shouldn't be any homework. That's my policy, but it fails. I didn't notice that. Yeah, before these 2 exams there'll be some homeworks, but at least let's say I made some arrangements to deadlines so that people still can work the exams if they want to do, if they want only exams study. What else? Okay, homework 6 is coming this evening. It will be next week, Thursday. Homework 5 is due tomorrow midnight. Okay, lots of homeworks and etc. You see. And in the homework 5, remember there are 2 questions about designing algorithms. And I received some questions about how to write it. It's not necessary. I will, present the solution in pseudocode format, but you do not have to use the pseudocode format. Since you are new to this business, I assume most of you are at least new. So either you can use the pseudocode, as described in the textbook, or you can describe your algorithms like this. Clearly state what the first step is. Right? Describe the second step clearly, like that. That would be also. You don't have to. It will be good if you say step 1, step 2, or just write it like this step-by-step manner. But for me, how are we going to grade this? We are going to grade it through the perspective of correctness. As long as the solution is correct, either this form, or pseudocode, they are all fine for me. All right. So please focus on finding the correct solution idea instead of focusing on the format. Okay. Of course, this shouldn't remain. And again, this is week 9, and in week 11, so 2 weeks after, we have exam 2. It is November 6th, if I recall correctly, but it's in the syllabus. So, all right, I don't remember anything else to announce. Any administrative questions before I jump into lecture? Okay. Because during if something comes to your mind, please save it until the end of the session, please. Okay, so today, last class, we started doing some number theory. I said that it would be a short introduction to number theory because this class is like an interdisciplinary subject, which borrows some topics or subjects from different branches of math and computer science. Number theory is one of these topics, and it's a deep topic normally. It's a very old branch of math. So we are just doing a very short introduction, and but that's enough to show us like how things can go crazy and how rigorous we should be, right? Like today I will do one more example from divisibility. Then I will start a new topic called principle of mathematical induction. Not introduction, but mathematical induction. So it is chapter 5. All right. So we are going to just see how things, go. So let me first finish the example from number theory. Then we talk more on principle of mathematical induction. So here is a theorem. Let m be a positive integer and okay, a is congruent to b modulo m, and b is congruent to d. No, did I say b? It must be c, sorry. Modulo m. That's given, that's what we assume. And then we claim that then a plus b, no, not a plus b, sorry, a plus c should be congruent to b plus d modulo m. So simply sum of left-hand sides is congruent to sum of right-hand sides modulo m. So summation is follows. Okay, proof. Since we are given a is congruent to modulo m, we get that m divides a minus b. So basically by definition, right? Do you remember this? Like last time we covered. And c is congruent to modulo d modulo m will mean again m divides c minus d. But then, good. We can now say a minus b is a multiple of m because it's divisible, right? M divides it. So that's what it means. Again, another definition, divisibility definition. And c divides c minus d should be a multiple of m2. But I shouldn't say k, maybe something else. In general, a t. Okay, good. Well, if this is the case, now we can conclude something like this. Not conclude, but we can derive another fact. A should be equal to b plus mk, m times k. And c should be equal to d times m plus t. Makes sense? Looks like now I have an opinion about A and another opinion about B. I can now sum up the left-hand side, right? It will be A plus C is equal to B plus D plus M times K plus M times T, right? Some arrangement, let's say, will be, let's say, B, if I put this into M parentheses, right, we get this. But the good news is this. Looks like A plus C minus B plus D is a multiple of M. Make sense? Let me just write it a bit more clearly. Well, again, now definition tells me M divides A plus C plus minus, sorry, B plus D. Almost there, right? One more step. Finally, we can say, according to the definition of congruence, A plus C is congruent to B plus D modulo M. That's the end of result. Right? Step by step, every step is justified by definitions or some simple facts about arithmetic. Good. So here is an exercise. Imagine we have the same theorem, but with a slight change. I will say here, prove the it must be exercise 15 because we had prove the theorem below. So only change is this. Everything is same. A times C is congruent to B times D. I can throw more exercise, but really I expect you to find them. For instance, A to the C, is it congruent to B to the D? Right? I mean, things like that. So many questions can be asked, but just a taster. The rest is up to you. Like you can find the questions. All right. So that was sort of it. Like mostly this discussion was from section 4.1. The other sections of chapter 4 is you're not responsible for them. Okay. So as I said, we can't cover all the topics. Simply, there are lots of topics to cover in this course. I don't know, the design is a bit shaky, but at the same time, like the whole degree is like based on many courses which require to cover lots of topics. So simply, we are always short of time. Like you come to algorithms, same thing. Lots of nice things to discuss, but simply we don't have enough lecture time, session time, and things like that. Anyway, so that will be it. Now, chapter 5 topic. So I think in 3305, discrete math 2, it covers more stuff like this. Or again, like I strongly advise you to keep your discrete math book around you when you take that course. So that's the textbook, but for other courses too. So then you can use your textbook as a reference because like since you are somehow dealing with it through this course, so in the future it must be easy to use it for other topics for deeper study. Don't go and search things on internet, please. First, your textbook. All right. Okay. Next topic, we were saying principle of mathematical induction. Again, I'm just covering things from section 5.1. The rest, like chapter 5 is long, but just this one. So this, first of all, is a background knowledge. Remember in chapter 1, we were talking about proof types. Among many proof types, I gave you only 3 of them, I guess. No, 4 of them. Direct proof, proof by contradiction, proof by counterexample, and also sometimes we use proof by contraposition, right? To prove P implies Q, you can prove negation Q implies negation P, so proof by contraposition. Another proof type is called proof by induction. So proof by induction is used so commonly in math. Imagine so that in a textbook like this, it has its own chapter. So it's used a lot. You'll see like today we'll do a bunch of examples. We will prove things. And really like, first, of course, it would be necessary to know these simpler proof types to be able to understand proof by induction. All right, but let's say what does mathematical induction say? So it simply says the following: to prove, let's say, P of n is true, or let's say to prove that P of n is true for all n we must do the following. Okay, what are those things? First, there is something called basis step. There we just show, let's say, that P of 1 is true. In general, we show that P of n is true for the smallest possible value of n. What do you mean by this? For instance, P of n might say something like this, or we can claim something like that. P of n is true for all n greater than 5. So then we don't need to talk about P of 1, right? Instead, we will say, yeah, fine. By the way, P of n is what? P of n is a predicate, which takes one element, right? One input. Like P of n can be, for instance, all even numbers is a multiple of 2. I mean, for 2, you take 2. Yeah, it's a multiple of 2. You take 4, it's a multiple of 2. But as you see, even numbers is a problematic, all even numbers, I'm saying. How many even numbers are there? Infinitely many. So you are trying to prove something, right? Prove a statement for all even numbers, a set which is infinite. I mean, if like proving, right, what you want to show is this, your dream here is this. You want to get, right, this. Yeah, if there are finitely many n's, right, if the domain is finite, good, just try all of them one by one and then that's it. But what if it is infinite? Right? Then principal induction, induction becomes very handy in that case. Let me just take this and, but okay, we are not done yet. There is one more step. It's called inductive step. It simply says, show that P of k implies P of k plus 1 for all k. Well, if these two are satisfied, right, then we conclude that for all n, p times n is true. That's like the benefit of mathematical induction. Again, remember, this saves you from trying all possible n values. Because all possible n values, there can be infinitely many of them. But principle, yeah, like this is used a lot throughout the history. It's been used. It's a very old principle. What else I can say? Just a note. Remember, we discussed a lot about how to prove such a statement. There are possible ways, right? contradiction, contrapositive, and also direct proof. If you recall, we said direct proof says, right? Direct proof is very simple. Assume P is true, right? Show Q is also true. So that was the idea. But now, as you see in the inductive step, right? Then what to do in inductive step? It says show that, but let's say what to do in the inductive step. We just apply this idea here again. We will say assume P of K is true. Next, show that P of K plus 1 is also true. Okay? Because after all, we are trying to show a statement of this form. I can just maybe, yeah, this one. Okay. Yeah, so of course, we needed to know some logic to make sense of it, right? That's why we don't introduce it right away. I mean, they dilute it. Like you might, maybe later on, you will see some classes where they explain this without mentioning any logical aspect of it, but really it's something logical, something that we discussed maybe 5 weeks at the beginning of this semester. So I can even write like in like this, write this in a very short form, like in the chapter 1 format. So I will say, you know, this logically we mean the following: P of 1 and let me open like for all K, P of K implies P of K plus 1. These two together implies for all n P of n. Yeah, you see, like logic is in action now. All these things that we said here, one page, is indeed this one line. So that's why we like first order logic more than English. So there was one philosopher that they asked him which language is the best language. He said predicate logic, because I mean, if it is up to him, he would use always this one. But of course, when you unfold it, right, you get all these long definitions. Or we have seen when you have such a thing, you can also write an inference rule, right? Like P of 1 is true for all K. P of K implies P of K plus 1 is true, then for all n P of n. So it's like it can be seen as an inference rule too. So this thing, right? Logic tells us this is a tautology. This is true always. This is a fact. Okay. Let's do now some examples. Let's see how much you will like it. So, example. Show that the sum of first and odd integers, or and positive, okay, just let's say, is n square. So we will show this by using induction principle. So it will be a proof by induction. But before doing this, just like always, right, whenever you attempt to understand a claim in math or in computer science or in science in general, you have to first make sure that you understand the background information. So, okay, first, Let's work on some related notions. The first, if I say the first n integers, right? We would understand this, right? 1, 2, n, right? If I say the first n even integers, you would see what? 2, right? This is the first even integer or even number. 4, and what is the nth even integer, even number? No, and even 2n, 2 times n, right? Yeah. Okay. Well, now let's come to this, the first and odd integers. What is it? Okay, the first odd integer or odd number, let's say, is 1. The second is not 2 but 3, right? 5 and that. What is the nth odd integer? It can't be 2n because it's even. Any guess? -1. I'll show you. Okay, we'll discuss this. It's not +1 and -1. Yeah, I started with 1 and okay, then that brings me also, let's say, we can take this and proceed, but I want to dig it a bit more. So imagine I give you numbers. I say that, okay, here is the sequence of numbers. So how to count, right? How to make sure that we are counting correctly, like we are taking the correct sequence, because this statement relies on it. So if I give you this sequence, then you would tell me, right, how many elements are in this sequence? If they increase 1 by 1 and start with 1 and ends with 10, how many? 10, right? Obviously. So how about this? Let's complicate a bit. 53, 57, I don't know, 61, and ending with, well, change a bit. 55, 57, and okay, 997. Divided by 2, you said? Almost there, very close. No. Okay, let me give you. So here, the generic formula I'll give, and then I'll exemplify more. So the last, okay, minus the first, plus the jump amount, which is 2 here. Okay. Then divided by jump. Like if you look at the first one, you said 10. Let's justify it. 10 minus 1, and it increases 1 by 1, plus 1. So 10 divided by 1. That's how you get 10 elements over there. How about this one then? 997 minus 53. The jump is 2 divided by 2. So then we would get what? This were 44, right? 944, 946 divided by 2. Then that would be 473, if I'm correct. Yeah. So there are 473 elements in that list. But that's the generic, especially if the list increases, let's say, steadily like that, 2 by 2. But this wouldn't work if you, for instance, take this list. but not good. For instance, square of, imagine they increase by, there is a rule like this. The first one is square, the second one is square, 9, right? The third element is the square of 3, 25. So then this wouldn't work because like by, apply, let's say it ends with, I don't know, 2025. This is the square of 45. No, 2025. This is the square of 45. Yes, there are 45, but I know it. That's why. But imagine you don't know what it is. So then how would you, let's say, find the number of elements here? This formula won't apply because this is like for only the source, this specific easy, or let's say the sequences which increase steadily, but still useful for us. So then let's apply this law idea. Is it really the case? I'm taking this, okay. 1, 3, till 2 to the n minus 1. The jump value is 2, right? So 2 to the n minus 1 minus 1 plus 2 divided by 2. So there are n elements over there. Okay, that's why it's not 2 to the n plus 1. Like it's not ending with 2 to the n plus 1. Okay, so far so good. Then we just want, right, enough background information, but just you. So we want to prove, let's say then, prove that 1 plus 3 plus that 2 to the n minus 1 is equal to n squared. All right. So why do we do this background stuff sometimes, right? Because we want to be able to see what we really need to prove mathematically. The earlier one is just plain English. Won't be able to work with it. So you have to bring it to the more rigorous terms. Okay, good. Let's do what now? Basis, right? N can be, right? There can be only one. So then if n is 1, so the sum is 1, but it's equal to 1 square. That's good. Inductive step. All right, first we assume P of k, right, for an arbitrary, let's say, k. But also, I always recommend one thing. You can write this, but you should know it. You should do it by knowing what you are claiming indeed. So this means what? 1 plus 3. 2 to the k minus 1. 2 times k minus 1 is equal to k squared, right? That's what we mean by assuming P of k. Now I want to show, right? Next step in the inductive section. Show that P of k plus 1 is also true. So then, okay, this was true. If this is true, true implies true is true. Well, let's see. Again, since we are new to this business, let me write what do we mean exactly, what we want to prove, right? 1 plus 3 plus k minus 1. These are the first n odd integers, but I now say the first k odd integer. So I claim now first k plus 1 or odd integers. So the next one will be 2k plus 1, right? And last one. Their sum will be equal to k plus 1 square. So I want to show this. I didn't show it yet. Is it the case? I will check. So let us now take left-hand side. Let's start from here. All right. We know that this one right here, this sum, by assumption, we know it is equal to k square. Do you agree with me, right? That's what I assumed, right here. Well, good. Then I can say k square plus, of course, this is not bothered. So k plus 1, sorry, 2k plus 1. So I hope that this step, right, is clear by assumption. So does everyone agree with me how I came from this right-hand side, left to the right? Right? Good. As you see, assumption is very handy, right? Otherwise, I don't know, without assumption, a direct proof would be impossible. But it simplifies my life quite easy. So now I will say the following. I just continue, right? This was parenthesis. K squared plus 2k plus 1 from your pre-calc, from your high school algebra arithmetic. What is it? What is it equal to? K plus 1 square. That's the result, right? This whole thing is equal to k plus 1 square. That's what we wanted to show, and we showed it. But remember, assumption plays a role. So we don't do it independently from the assumption. We can do it, but it could be an overkill. Instead, we abuse it or we exploit that fact, right? As soon as we jump to that. Good. So now we can say safely P of k plus 1 is true. And the claim, since we now took care of these two steps, right? Now we can say that this claim is true in general. So I can write something like this. For all n, P of n is true. Good. Okay. Next, let's do some more examples. Yes. No, you don't have to do that way. But I did it here because I want you to understand that such a proof becomes understandable or possible only if you know some facts. And imagine you are alone without me. I mean, you don't have to write it in the homework, but some things have to be appreciated, have to be seen first to be able to proceed. But in the homework things, don't worry about it, or in exam settings, just look at that. Still, you have to provide clear explanations, but doesn't mean that you give all the background information starting from gas cloud to that. No, that's something short. Okay, next is this one. Show or prove that n is less than 2 to the n for every positive integer. I mean, intuitively, I think you agree. Also in the chapter 3, right, we said n grows slower than 2 to the n. But how can this be proven by just using induction? This time, not like it is asymptotic analysis, but with a proof by induction, we will prove it. So is there anything to refresh our mind here? No, right? Just numbers. We know, right, more or less. So if necessary, we would work it out. So I say proof by induction. So I signal that I'm going to have now 2 steps, right? Basis. Okay, positive integers. Again, what is the smallest possible one? Like 1. Or at least this set starts with 1 and goes on and on. P of 1 is true. But again, we have to justify, let's say, with an explanation like this. For instance, 1 is less than 2 to the 1. Okay. Maybe I can take it here. Obvious reason, right? Obviously. So base case false. Good. Second, inductive step. Again, I assume P of K is true for an arbitrary K Z plus, right, in the set. Then, since again, and let me say what it means. So we just simply say, right, this one, K is less than 2 to the K. That's what we imply by assuming that. Now, we want to show that P of K plus 1 is also true. How do we do that? So it means, right, showing that it's true, K plus 1 will be less than 2 to the K plus 1, the exponent. So we need this, but how? Let's see. We can, we know this fact. That's by assumption. We start like this. So can I just add 1 to each side, right? The relation will be preserved. So they have this less than relationship. So I can easily claim that K plus 1 is less than 2 to the K plus 1, but this one is not in the exponent. I want this, but not close yet. Well, good. We know that this will be, right, 2 to the K plus 1 will be less than 2 to the K plus 2 to the K. Well, did I confuse anyone here? Okay. But remember, this isn't accidental, but I want to reach, right, like something like this, first of all. So for that, I need to make an observation. So let me just borrow this, and each time you write a proof, right, you have to really. So this is a step, right? Like this is this step. How can I justify it? So do you agree with me that, right, this can be ignored? So then, to claim that this step is legitimate, so I need to show 1 is less than or equal to 2 to the K. But isn't it true? Like imagine the K values is all these positive integers. Like, okay, if K is 1, 1 is less than or equal to 2. True, right? If it is 3, 2, yes, same. So it holds for all the possible values. Then, right, my claim, right, this step is justified. I mean, if you have this, let's say, 2 to the K, so you can add 2 to the K both sides. You would get this, right? This step. Okay, justification, right? We have to arithmetic, but still like a small justification. Good. So let's take this here and say, right? So, I mean, recall. Well, this thing is now equal to 2 times 2 to the K. Then it's equal to 2 to the K plus 1. So then using all this transitivity, right? Like remember, K plus 1 is less than this, which is less than this. So through the transitivity, we can claim that K plus 1 is less than 2 to the K plus 1. Okay, makes sense. So are we good? Like, is every step justified in your mind, right? We shouldn't proceed without justification. So like, I hope that that's clear. Like I say, this reasoning is like this: A is something less than B, B is equal to C, which is less than D. So then wouldn't you say here, right, in this way, right? You would say A is less than D because of transitivity, right? That's what we do. Like the statement is of this form. So here, then K plus 1 is less than this quantity here, but it is less than this and it's equal to something. So, okay, good. Let's do one more thing. 2 to the n is less than n factorial, but careful. For all n greater than or equal to 4. It doesn't consider 1, 2, 3 because this claim, right, doesn't hold. 2 to the 1 is not less than 1 factorial. Or 2 to the 2 is not less than 2 factorial. So it's only, it starts becoming true only after 4. All right, like let's do, it's almost similar, but induction. So basis P4, not the others, is true because, or since 2 to the 4, which is 16, is less than 4 factorial, which is 24. Inductive step. Assume K is true. So it means, right, K is 2 to the K is less than K factorial. And we want to show P of K plus 1 is true. Simply we want 2 to the K plus 1 to be less than K plus 1 factorial. That's what we want. How come? So if you take 2 to the K plus 1, we know that it's equal to 2 to the K times Q, right? For sure. But now let's focus on this one here. Keep this. If I multiply both sides 2 with 2, do you see what we get? So can I now claim, like, based on this fact, this will be less than K factorial times 2, right? Justification again. Observe and then apply. But then, can we write, like, let's say here, recall all the time, okay? So, okay, oops, no. Another fact to remember. How about this one? 2 is less than K plus 1 for all K greater than or equal to 4. So those are the values that we are interested in after all. Isn't it true? Right, all the time, for every possible K values that I can take, 2 will be less than K plus 1. Okay, good. But then if I multiply both sides with K factorial, right, I would get K factorial times K plus 1. Okay, so then what? This is less than K plus 1 times K factorial. But this I know is equal to K plus 1 factorial by definition, right? me just take this a little bit down and say here. So then from here, I conclude that 2 to the k plus 1 is less than k plus 1 factorial. That's the result. Come in. Makes sense? Okay. Second fact. Yeah, just like after the class, please read these and play with it. And if you have questions, you can let me know. But I hope that like these are kind of early examples. So there are more complicated ones. For instance, let's do an example about divisibility, which we covered recently. Prove that n cubed minus n is divisible by 3 for every n in positive integers. Okay, so simply it's asking us to show this 3 divides n cubed minus n. That's what we will show. So, or let me write like this, P of n, right, according to the principle of induction, is this thing. That's what we need to show somehow. Okay, proof. By induction. So the basis case. And the smallest n value is 1. P1 is true. But of course, that's not enough to say. Let's show it. N cube, say 1 cube minus 1 is 0, which is divisible by 3. So do we have a problem with this? That 0 is divisible by every number, because 0 can be written like any number times 0. So it is divisible. Because when you divide 0 by any number, you get remainder as 0. So that's the thing. That's why. But 0 does not divide any number. It's undefined. Good. So this case, easy to check. Inductive step. So assume P of k is true. So it means 3 divides k cubed minus k for an arbitrary k value, which I don't want right now. Show that P of k plus 1 is also true. So simply we try to say 3 divides k plus 1 cube minus k plus 1. So just like a note. So all we try to show is this then, like as a logical statement. We try to show that if 3 divides this, right? If this is the case, if this is true, then it implies that 3 divides and we said that such a statement is proven like in these 2 steps. First, assume this is true, then show this also. Okay, so fine. Then let me take this statement. After all, that's the trouble here. Okay. if I expand it, right? Sometimes, you know, you try all these things, but the easiest thing to do here is to expand or unfold this. Let's say k plus 1 cube will be expanded like k cube plus 3k squared plus 3k plus 1 minus k and minus 1. So I can rearrange this a bit without destroying the equality. Say k cube minus k. So I can then put, because since I'm after showing divisibility by 3, so I see some terms with 3, so I can put them into 3 parentheses. K squared plus k. And this minus 1 plus 1, right, cancels each other. Their sum is 0. Also 0 is divisible by 3. So looks like we are left with this. But now I can say, note that 3 divides k cubed minus k, right, by assumption. And also 3 divides 3 times k squared k. After all, this is true, right? 3 always divides any multiple of 3. Right? 3 times anything will be divisible by 3. But but these are the 2 components of this huge sum. So then the whole sum is divisible by 3. Remember, we said once, if A divides B, if A divides C, then A also divides B plus C. Right? This was one of the facts that we proved. So then I can conclude 3 divides k cubed minus k plus 3 times k squared plus k. But of course, this was equal to what? K plus 1 cube minus is k plus 1. But that was right. That's from here, right? This is equal to that. Hence the result. So then we can just write a bit more like saying P of k plus 1 is true. So then that's it. Make sense? Any question? Okay, no question. One last example. This time, let's change the topic a bit and let's switch to set theoretic fact. So we want to say the following. So we know that you know, power set A be the set of all subsets of a set A. We know, we discussed this, right, in chapter 2. A set will have more than one subset and like things like that. And we want to show that cardinality of power set, okay, this is called power set, is equal to the cardinality of A. Like if you recall, there are 2 elements in the set. The number of its subsets was 4. Right? Do you remember this, everyone? If there are 3, then there will be 8 subsets of it, including the set itself and the empty set and the others in between. 4, 2 to the. But I mean, how many sizes are there possible for set? Like infinitely many. So then how do we show it like in general? Because I mean, I can tell you, or I can prove the result manually or in brute force for 100 values. But if you give me the 100 first, then I have to again do the same thing. So again, proof by induction will come handy here. But okay, let me write proof by induction. Now, in this domain, in this discussion, what is the smallest size possible? 0, right? Not 1. Okay, then P0. Is true. Because if the set is empty, it will have only one subset, the empty set itself. That's it. So let me write, let's say, since the empty set has only one subset, right? I mean, like, I hope this is clear. If this is the set, right, a set is empty, then okay, empty set is a subset by definition. Now, let me just write it. Let's say A is empty set. So I want to find the subset of this set, all the subsets of it. Okay, by definition, we said that empty set and the set itself should be in the set. And there is nothing else to consider, right? That's it. Looks like 2, but remember, A is also equal to empty set. So we have this indeed. What were we doing when we have this? Just 1, right? Multiple occurrences do not count. So what is the cardinality of this set? It's 1. That's why. Good. So I hope it's clear now. All right. Inductive step. So assume okay is true. That means, right, if A's cardinality is K, then it will have 2 to the K subsets. That's what we assume. Of course, I should put the cardinality sign. Good. Imagine, now, yeah, okay, one more thing to say. Show that P of K plus 1 is also true. So I can, since I already have a set with K elements, if I add one element to it, let's say, let us add one element to A. So simply, I mean, consider this new set. A is new, right? A is an element. But then this set has cardinality what? A has cardinality K, the new element joined. So we have this one. K plus 1. Oops. All right. So we want to, okay, one observation. Power set of A will be a subset of power set of this new set. Isn't it true, like, okay, you expanded the set, but all the subsets, right? All the subsets of A will still be subsets of this new set, but also there'll be new ones because of adding this new element. Am I clear, or should I clarify more? Okay, but we will illustrate it in any case. So 1 second. So let's see. For each subset of subset, let's say X of A. We have exactly two subsets of this expanded set or extended set. How come? First, X will be a subset of this one. But also, X extended with this single element will be a subset of this one too. So let's put this like in parentheses to make sure that they are same set. So let me, if this is not clear, let's do a small illustration. Imagine, let's say, A has these elements, 1 and 2. So what are the subsets of it? Like we can enumerate it, right? 0, A itself. Or let me write, A itself like this set form. 1 and 2. These are the subsets of A, right? So now I take, all right, I expand A with this. So won't all these be subsets of this new one? Do you agree with me on that, first of all, right? These are all subsets of it, right? Subsets of it. Yeah, 1, 2 is a subset of, I made a tiny mistake. Okay, right? This set is a subset because it's here. These are all subsets, but we have new ones. According to this recipe, right, all these can be expanded. Let's say when you take, you will get here A, here you will get 1, 2A, here you will get 1A, here you will get 2A. But then what happened? Those are the all subsets of this new set. How many of them are there? 8 in total, right? So looks like, therefore, cardinality of power set of, let's say, A union lowercase, this expanded one, is 2 times cardinality of power set of A alone, right? Because it was 2 and then it became 8. But we know that power set of A, by the assumption that we made, is 2 to the k, and 2 times 2 to the k is 2 to the k plus 1. That was what we tried to show. Right? We assumed that this is 1, right? And then k plus 1. So we will say, therefore, k plus 1 is also true. Okay, everybody? So this, you see, like, depending on which domain you play with, we have to make some observations and things like that. This set theoretic proof, right? We construct it like we through an example and things like that. Simply, it says when you add one element to the, let's say, to a set, then the number of subsets doubles. So you don't have to worry about adding 2 elements then. So there was a question in the morning, what happens if we add 2 elements? No worries. First, add 1 element, calculate, right? See it doubles, and then add the second element, see that it doubles. So then you can conclude that it will quadruple. If you add 5 elements, then the number of subsets will increase how many times? 2 to the 5 times, right? 2 to the 2. So as you see, principle of induction is very strong. It saves a lot of work. First of all, it simply ignores the other cases, like we don't worry about the step after next, like k plus 2 is no problem. After all, to reach there, first you have to go to k plus 1. You take care of it, then you go to k plus 2, because p of k plus 1 will imply p of k plus 2, and that will imply p of k plus 3, and so on and so on. So it simply says, do not jump, but instead go step by step and go as much as you want. Very strong principle, and it's very old. Okay, let this be enough. So tomorrow, for those of you, with those of you who can attend, I'll talk to you there, right, at 10 a.m. for the problem solving session on MS Teams. It won't be physical. Otherwise, yeah, like you can listen to the recording and things like that. All right, thank you so much. All right, chatroom, you have a good day too. Bye-bye. Yes. Sure.
For number 32, it's the one